Anyway, let's go on. What I want to do first is diagonalize the mass matrices. That's pretty easy. The more fun will be is I'm going to do the neutrinos also. Okay, so neutrinos are going to be more fun. So first, where we ended up last time, we had the Lagrangian turned into minus 1 over the square root of 2 v plus h times a set of matrices that would be like things like gamma u I j, u bar I, u j, plus things with other ones also. So that's a full matrix there. And we'd started off calling these things, ui is u, c, and t. But at this stage we can see our mistake. Those guys are not states of definite mass. So let's call them instead u0, c0, and t0, being they're just some names. And then our Lagrangian, the mass terms look like this. So you have Lagrangian has minus v over the square root of 2, so that's times u bar 0, c bar 0, t bar 0, gamma 1, 1, gamma 1, 2, etc. Of u0, c0, t0. So how do we solve this? Well, of course we diagonalize it. There's something interesting about diagonalizing, though. This matrix is neither real nor Hermitian. And actually, it's important that I did drop some notation here. This was L and R, L, R, and there's a Hermitian conjugate, couples right to left. So those elements, every one of them can be complex. And so we don't really have good theorems about diagonalizing that general matrix. But we'll see that we can turn it into ones that look like our usual diagonalizations. So we're going to define these u0 left, it's some s left, u left. This is going to be a unitary 3 by 3 matrix. Likewise the rights. And we then have, we've got twice as much freedom in diagonalizing this, and that allows us to do it. So our goal is, if we start with m0, which is v over the square root of 2 gamma as a matrix, we want m diagonal is SL dagger m0 S right, and we'd like that to be mu md ms. Okay, can we do it? So here's the connections to theorems that if you consider first M diagonal squared S left dagger M0 S right dagger M0 S left. That's S left dagger M0, actually this should be daggered, M dagger S left. Now we know that we can diagonalize, this is now Hermitian matrix, and so we know we can diagonalize that by unitary transformations. So S left diagonalizes M0 dagger, which is a Hermitian matrix. If we do the other combination, you put it in the reverse order. S right diagonalizes M0 dagger M0. So we choose those to be those matrices, that's also Hermitian matrix. It's not the same one necessarily. It's the Hermitian conjugate. And the eigenvalues have to be the same. So that implies that you can diagonalize it. Okay. Okay. So we diagonalize that guy. Okay, that's fine. So this then lets us get states of definite mass. Okay. The neutrinos are different. So actually, anyone want to ask questions before we get to neutrinos? Okay. If we start off with minus v over square root of 2, neutrino left, gamma, neutrino right, that's the same story. Okay? However, there's something else that you can do with neutrinos. Okay? But there's that the neutrino right is a singlet. Under all the gauge groups. Okay. So that says if we form a Majorana mass, it works out okay. Okay. The Majorana mass term is minus m sub Majorana psi bar. In this case, will be right. There's the actually, I'm sorry, psi right, no psi bar, psi transpose, I gamma 0, gamma 2, psi right. Okay, so we saw that when we did Majorana masses. That's if there was a charge Does everyone see that if there's a charge, you couldn't do that? So if there was if it carried any charge, since this is psi and psi, if you take e to the I alpha psi, this would change by e to the I 2 alpha, because so you couldn't do this with the left-handed neutrinos. You can only do it with the right-handed neutrinos. Okay. So, in the spirit of if it's not forbidden, it's required, we should add this term. So this term is certainly allowed. So let's add it. Okay. So there are two terms. Then the Lagrangian contains the minus v over the square root of 2, nu bar left, gamma nu right, and then there's I'll put it as a matrix minus. So we can write this as nu bar right conjugate Majorana mass matrix nu right. Okay, so this is psi bar conjugate. That's sort of standard notation. You just okay, and this in principle can be a 3 by 3 matrix also. Okay. So what's the effect of that? Let's deal with just one flavor. The mass matrix then has the following form. It's nu bar left, nu right. Let's see if the notation here gets a little complicated, but nu left, nu right. This is actually nu bar left conjugate. In this picture, there's no coupling of nu left to nu left. There's a Dirac mass, usual type of mass, connecting nu left and nu right. There's a Majorana mass connecting that term. So in addition to the 3 by 3 diagonalization, which we'll do secondarily, I'll do that one afterwards, there's a diagonalization among these states. The common solution to take for this is the Majorana mass much bigger than the Dirac mass. Okay. If you do that, the eigenvalues are m1, which is then m Dirac squared over Majorana mass, and m2 is the Majorana mass minus okay. So it's one drops that. Okay, and the mixing angle between left and right is M Dirac over M Majorana. Okay, so this pattern here goes by the name of the seesaw. So the picture seesaw is big mass, little mass on this seesaw. Has that feature, and it's of course taken to be explaining the small masses for the neutrinos. So if you have M neutrinos, they tend to be about something like 0.05 electron volts. If that's ME squared, that's the Dirac mass, over, it turns out to be 6 times 10 to the 10 GeV. So if you take the Dirac masses to be over the electron mass and the Majorana mass over 10 to the 11 GeV, you get neutrino masses in the right ballpark. Okay. Questions? Let me I want to redo this. First thing I want to do is really redo it as a dimension 5 operator. Okay. Which is useful way of thinking about it. Remember, if nu right is of order, and Majorana is 10 to the 10 GeV, you can integrate it out. Okay. So if you integrate it out, then you're only going to be left with your light fields. So here's what happens. The Lagrangian that you start with has minus gamma, a doublet, the lepton doublet left, phi bar nu right, minus nu bar right, conjugated M Majorana nu right. Okay. The goal then is to integrate out nu right. Okay. Pictorially, what we're doing is you take psi left, Higgs nu right. There's a coupling that comes from that term. We lowest order you integrate it out by just putting a propagator there. Psi bar, psi left, phi nu right. So just like we normally often do W exchange or heavy S exchange in a sigma model, we do nu right exchange here. This leads to an effective Lagrangian that has minus gamma squared gamma over M psi bar left, phi bar that's the one coupling. The propagator is the 1 over M Majorana, and then we get phi bar, psi bar left conjugated and you get a Hermitian conjugate. Okay, so we get an operator like that. This is dimension 5. Psi bar psi is dimension 3, phi is dimension 1. So it becomes dimension 5. It's also gauge invariant. Because this guy is a singlet under all the gauge symmetries. You can see it looking up here. This was a singlet, so this one is also a singlet under all gauge transformations. Okay, so there's this operator. And then after symmetry breaking, phi goes to phi bar is V in the upper component. This thing turns into minus gamma squared V squared over 2 M Majorana psi bar left, psi bar conjugate left. Actually, I'm sorry, this is only neutrino left. And then this is our Majorana term. Okay, so this guy is M Dirac squared over M, like before, and you get the same old answer. Okay, so you reproduce the same thing as the seesaw. This is typically thought to be more general. You could imagine other types of interactions also generating a dimension 5 operator. So you shouldn't add it to the usual Lagrangian, but it generates this. It explicitly shows that the mass terms that you end up coming out with here, this guy is the mass term for the light particle. It's equivalent to a Majorana mass. Okay, because it's dominantly left-handed. Okay, so what's sort of funny about this is that the one way of doing it up here, we started off giving Majorana masses only to the right-handed particles. And then you do the eigenstates. Down here, the Majorana mass shows up in a gauge invariant form, but with the left-handed particles. Those are actually totally equivalent there. Okay. Questions? So, with that, let's do Majorana neutrino mixing now. So now we go back to the 3x3 case, and we have 0 M let's call M0 diagonal, Dirac, M0 Dirac, M0 Majorana. Okay, so the Dirac ones are completely general 3 by 3 complex matrices. Majorana has to be 3 by 3 symmetric. Okay. It's symmetric because it's new right coupled to new right, so that those fields are symmetric. Okay, you integrate out the Majorana. You get M for the seesaw is M0 dot Dirac 1 over M0 Majorana M0 Dirac transposed. Okay. Okay. We know that we can diagonalize the Dirac one. Okay. So we write this as S left M Dirac S right dagger where this one is diagonal as M Dirac 1, M Dirac 2. But those are not the physical masses, so we have to hold off a little bit. I'm not going to call them M1, M2, M3 because that's going to be our end answer. Okay, so let's imagine we know how to diagonalize that. What's left over? Well, so now M0 seesaw is S left M Dirac, which is diagonal, S right daggered 1 over M0 the Majorana mass S right transposed M Dirac S left transposed. Okay, this in the literature is often called the central matrix, C. Okay. This needs also to be diagonalized. So need to diagonalize this. So C is going to be chosen to be some F M nu F dagger F transpose, where this guy finally is going to be the diagonalized one. This is going to be M1, M2, M3 is the physical states. Okay. So you can do it. So that's fine. So we finally diagonalized. But the overall left-handed transformation is new right is S left F. It's this guy's from the Dirac Matrix. This guy's from the Majorana. Okay, so we have two terms there, one reflecting the Majorana part. Okay. Any questions there? All right, let's then do the effects of the diagonalization. In the charge currents, in the neutral currents, there's no effect. It's easy to see. Let's take the electromagnetic current, is the charge is in general psi bar Q gamma mu psi, where Q is the mass matrix, so it starts off with 2/3 U bar 0 left gamma mu U0 left plus C bar 0 left gamma mu C0 left plus T bar 0 left gamma mu T0 left plus left goes to right plus other charges. Okay, so we have since the left-handed and right-handed rotations are separate, these guys are singlets, and so that just turns into then the same thing, but with the physical fields. So it's no longer U0. Left and right both enter the same way, gamma mu U C. So the rotations have no effect on any of the charge currents. The Z current is also the same way. The charge currents, of course, have this if I have the charge W coupling to U bar 0, C bar 0, T bar 0, coupled up to this is left-handed currents, gamma mu D0, S0, B0. This turns into the couplings UCT, left mu VCKM DFB VCKM. Actually, I may have written the definition backwards there, but it's no, it's actually the right. Is then S for the up-type quarks daggered, S left, S for the down-type quarks left-handed. Okay. So this is the VCKM matrix. The neutrinos, leptons, have a slight difference there. It's the equivalent mixing matrix is F dagger, F neutrino left, F electron right. But the net effect is not much different, even though there's a new matrix there. It's also still 3 by 3 unitary. Okay. This is the Pontecorvo Maki Nakawa Kita, I think, matrix PMNS. Let's quickly do the parameter counting. Okay. So it's unitary 3 by 3. That implies 9 parameters. But you can remove some of these. Some of these parameters are unphysical. Okay. You can, for example, so it's 3 by 3 with complex elements. You can make the diagonal elements real by choosing, you know, U goes to e to the I phi U1, U, C goes to e to the I phi 2, C, T goes to e to the I phi 3, T. So you can make the diagonal elements real that way. So 9 has gone down to 6 by doing that. There's still some things you can do. Then you could make, so this might be the first step, 2. If I wanted to make VUD real, it's a common choice. You could change D goes to e to the I phi D Okay. To do that, you'll have to readjust the phi 1, phi 2, phi 3, that's phi 4, to keep the diagonal elements real, but you can do it. So now we've down to 5 parameters. There's one more available. The relative phases of T and B. You can make BCB real. Also. So we end up down to 4 parameters. And you can't make any further changes. So this V matrix can be put into the following form. It's real, 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 real here, complex there. Okay, and then the rest of them are fixed by unitarity. Okay, that's a possibility. This a real 3 by 3 matrix has 3 parameters, 3 Euler angles. Here there's going to be 1 phase. Okay, so that gets us into our standard form, and the pattern that seems to be in nature is 1, 1, 1, roughly on the diagonals, small there, smaller there, and yet smaller there, with a phase. This is now an experimental pattern. Okay. Again, for neutrinos, the story is a little different. It's almost the same, but if there's a Majorana mass, then you can't do all the rephasing. If you can't rephase nu left because if you know the term nu left transpose nu left is not invariant. So then the PMS and S has sort of the same form, 3 plus 1 phase there, but there are in principle 2 other phases. Here e to the I alpha 1, e to the I alpha 2, and the overall phase still has no particular meaning, so you can choose that. So there's 2 extra phases which you can remove or not depending on whether the mass is Majorana. But that's then interesting. It's then these phases are unobservable except if you do Majorana masses. So unless you do something with Majorana masses, you can't see them. Okay, any questions about that? So these extra phases are present there. I don't know if I should bother spend time on the parameterization. Let me maybe just give you the Wolfenstein parameterization of this so we can use it. Where is it? Wolfenstein parameterization, the VCKM matrix is 1 minus lambda squared over 2, lambda minus lambda, 1 minus lambda squared over 2, 1 a lambda squared, a lambda cubed, rho minus I eta, minus a lambda squared, a lambda cubed, 1 minus rho minus I eta. Okay, so in this parameterization, lambda is 0.22 to the best we measure it. A, actually I don't have the numbers here exactly. A is order 1, rho and eta are of order 1. I think rho squared plus eta squared is about a half, I think it is. Okay. Any questions about that? Let's set it up. The first thing I'd like to actually do with it is weak decays. The tree level diagrams are trivial. So example, let's take B goes to C, C bar S. Draw the picture. This is a W minus. The interaction is weak Hamiltonian is G2 squared over G2 over 2 squared root of 2 quantity squared, 1 over MW squared, V CB, V star CS, B gamma mu, 1 plus gamma 5, C bar, gamma mu, 1 plus gamma 5, S. S bar, I'm sorry, this is silly. C bar, S bar. Okay. So the tree level is trivial. The deeper level is very complex. because you can have all sorts of diagrams that look like gluons here, C bar C, gluons going across there, gluons going across there. Etc. So this is where we go to the operator product expansion to calculate all of those effects. And I'm not sure how much I'm going to get time to discuss that in detail here. The leptons, however, are easier. The effects of higher order things are much weaker. So let's just give the example. If I want mu goes to E, mu goes to nu E, nu bar, muon decay. So this is mu goes to some neutrino I, some antineutrino J. The Hamiltonian for that is G Fermi V J I V star I mu J electron, sorry. E bar gamma mu 1 plus gamma 5 nu J nu bar I gamma mu 1 plus gamma 5 muon and the decay rate for that has the following form. Let's just write it out so we have a bunch of things to talk about. Mu goes to E nu I nu bar J is, it's a pain to calculate. G Fermi M mu to the fifth 192 pi squared V J E squared V star I mu squared. So then there's a bunch of terms. There's, starts off with a 1. There's a piece that's relevant for the electron mass. It's minus 8 m e squared over m mu squared. There are higher order terms like that. There's corrections that come from the W propagator. It turns out to be 3/5 m mu squared over m w squared. There's terms, I actually don't have the exact number here because it's so tiny that no one calculates it, but it'd be m nu squared over m mu squared, corrections with some number there. And then there are corrections due to electromagnetic interactions, alpha over 2 pi, pi squared minus 24 over 4. So there are all these various corrections. Most of these are small. This guy is 10 to the minus 4. The electron muon mass is very small. The propagator correction is of order 10 to the minus 6. The neutrino mass correction is of order 10 to the minus 15. So that's pretty negligible. And this guy is 4 times 10 to the minus 3. So even that only enters if you need to do the precision test. Okay. These guys disappear, the VCKMs, if you don't measure the neutrino masses. If you don't measure which type of neutrino it is, you have sum over I and J, V J E squared V I mu squared is 1 by unitarity. The total decay rate then turns into G, sorry, that was G squared, M mu to the 5th, 192 pi squared. And we just define that to be G mu squared, and this tells us that G mu, this is what our best measurement, 1.16637, 2 in the last digit, times 10 to the minus 5, GeV minus 2, which memorizes 10 to the minus 5 over the proton mass squared. All right. So I think I'm going to stop right there. Let's stop there. My game plan for the remaining standard model is I actually have a lot of things I want to do. So we're going to have to see how well we can go through it. I basically now to set up the model, I want to do a little bit on flavor changing processes, rare flavor changing processes. I want to do a little bit on the construction of the chiral Lagrangian for QCD. I'd like to do a little bit on W and Z physics leading into new physics. Okay, so that the transition will be to do these two explorations of this standard stuff and then start looking at how you see new physics away from the standard model. Okay, and then those are my next two classes. So there's two classes on that phenomenology, two supersymmetry, two gravity.